אוקיי, טוב, נתחיל. נשארו לי כבר 25 דקות, אז I have 25 minutes left, so I'll try to speed things up. But in any case, I'm at the Lumigo booth outside, so if I don't finish everything and anybody has any questions, feel free to catch me outside, and I'm happy to answer whatever is left of this talk. So, hello everybody. Really happy to be here. My name is Or Weinstein. I'm VP of Product at Lumigo. Lumigo helps developers troubleshoot their applications in production. We'll talk a little bit more about how we do that in this talk. And today I'll be talking to you about how we built our Kubernetes operator. A little bit about myself. I started my career as a developer in the Israeli military, spent some time in product management at AWS and Google Cloud, and today I'm VP of Product at Lumigo. So, what will we be talking about today? We'll spend the majority of our time talking about how we built our Kubernetes operator and what it does. But to get you all there, we have to start with some context. So, what is distributed tracing? Why is it so hard to get done right? And why did we go to the lengths of building everything that I will show you today? So, where do we start? We start at the beginning. At least years back, most applications were built as monoliths, right? They have many disadvantages, which is why we switched at some point to microservices. But they have one glaring advantage. That advantage is they are much easier to troubleshoot. They run on machines or VMs. You use logs and metrics. They all come from the same place. Relatively easy. Nothing is easy in production, but relatively easier. Now, we rightfully switched to building microservices, which have many, many advantages. I won't go through all of them right now, but one glaring disadvantage. That disadvantage is they're much harder to troubleshoot. Now, they are much harder to troubleshoot because virtually any flow in most modern applications consists of multiple services talking to each other. Now, if you look at the graph on the screen, there is one red node colored at the bottom. That's where the error is. Now, the root cause for that error isn't, in many cases, in that same service. It could be 5, 10, 15 services upstream from that in that request flow, right? So we have an error downstream. You have the root cause somewhere upstream, and good luck trying to find that root cause using logs and metrics the conventional way. It's much, much, much more difficult. And that is why distributed tracing came into the picture. And for those of you who are not familiar, distributed tracing is basically provides you with visibility into that entire request flow end to end. So a visual representation of those services, which service is calling which service, the latency, metadata, payloads, a lot of things that you can attach to these services to be able to visualize that request flow and debug in a much more easy fashion. Now, how do you do this? You use something called, very high level, something called the trace context, which gets created once upstream, ideally, and then gets propagated downstream to all these services to be able to correlate and create that visual picture somewhere in some backend. It can be Lumigo, it could be another system. Now, for that to be possible, each service has to have a tracer, right? A library, some means of collecting the data, processing it, and then transferring it to some backend system, right? Now, distributed tracing disproportionately benefits from the network effect. In other words, the more you trace, the better the insights, the better the visibility, the more holistic picture you get for your application, for your Kubernetes cluster, in this case. Now, it sounds easy, but it's actually very difficult. Imagine you have a cluster, multiple namespaces, multiple objects, different cron jobs, deployments, daemon sets, etc. Hundreds of these objects running in your cluster. You have to go one by one. You have to instrument these objects with the right tracers, right? If it's Java, you have to have the Java tracer. If it's Node, you have to have the Node tracer, etc. And not only you have to do this for all your existing objects, pods, I'll just say pods for simplicity, in your cluster, you also have to build a process to make sure any new pod, any new application that spins up in your cluster gets instrumented as well. right? So if some developer somewhere in your team spun up an application, didn't trace it, didn't go through the proper channels, didn't trace it properly, good luck when that application now has a problem in production. And that's what we experienced with some of our customers that came to us. So we saw that in many cases, you think you have everything covered, but when you have a blowout in production, you actually are missing that critical piece, that critical instrumentation, that critical trace from that application where things are blowing up. And so we saw this enough times at Lumigo where we made it our mission to basically say, we want to make it stupid simple to trace everything. We don't want it to be complex. We don't want to have our customers add lines of code. We don't want it to be any harder than a few simple operations that get you up and running in a few minutes. So that was our mission. We basically wanted our customers to be able to say, Lumigo, trace me this thing. In Kubernetes, we elected for the namespace construct. So trace me this Kubernetes namespace and be done with it. So we did some research on how best to go about this mission. And we stumbled upon the Kubernetes Operator. How many here in this room, raise your hand if you've heard of what an operator is, you've dealt with it, you've played with it? OK, most of you, great. So very briefly, an operator is just a means of extending the Kubernetes functionality. And another benefit is it's very easy to reuse and share with other developers, with other teams, companies, et cetera. Now, operators are used out there for many, many, many different reasons. They have many benefits. For our intents and purposes, we like the fact that it basically helps automate complex manual tasks and operations. Right? That's what we wanted to do for our customers. So we built the Lumigo operator. And in the remaining time I have with you here, next 18 minutes, according to this clock, what we'll do is we'll walk through what the operator does for our customers, and then how we built it, right? What's the magic underneath? So at a very high level, we'll dive deeper in a second. The operator does three things. The first thing is it instruments existing pods. So all the pods, objects you have in your namespace that you chose to trace, it automatically injects them with the tracers. Now, it also makes sure that any new pod that gets spun up gets injected with the right tracers as well. And lastly, it's very, very seamless and easy to clean up, meaning you decided you don't want this namespace to be traced anymore. It's very easy to untrace everything, and Lumigo takes everything away and leaves no trace that it was ever there. So how does it actually look like? What does a user have to do to get a namespace traced? Two things. The first is install the operator using Helm. So Helm repo add, Helm install, very seamless, very easy, just like any other Helm chart you would go about installing. So first is a Helm install. That basically takes the operator and puts it in your cluster, right? Now, the next thing the user has to do is add, and you probably can't see anything here, but I'll just talk about it, is to add a custom object or a custom resource that we created to the namespace you want to trace, right? Around 12 lines of code through your YAML or through kubectl apply, whichever method you prefer, but add the custom resource to the namespace. You also have a Kubernetes secret here, basically just to keep the Lumigo credentials, the token we use to authenticate to the Lumigo backend. But that's it. You're done. So your Helm installed, you added a custom resource to your namespace, and now your namespace is traced. Now, what does that mean? Think of this slide as your cluster. The operator, the Lumigo operator, is installed in your cluster. You then have your namespace, where you put the Lumigo object in. And all the Kubernetes objects, all the pods, get automatically instrumented with the right tracer. So if the pod is running a container running Java, you'll get a Java tracer. If it's Node, you'll get a Node tracer, et cetera. Now it gets interesting. So how does this work? We'll spend the remaining time answering these 4 questions. So the first one is, how do we get the tracers into the containers? Right? That's the basic first thing we have to do, get the tracers into the containers. But that's not enough. Once we get the tracers into the container, you have to load them into the process. Right? So how do we activate them? How do we do the equal of, in Node.js, the require, in Python, the import? How do we load the package into the process so it can be used? Then, how do we make sure every new pod that spins up gets injected with those tracers? And lastly, how do we clean up? So let's start. Here is a kubectl describe of a one-liner Python container. Right? Very, very simple. Nothing special here. I cleaned it up also so it fits on this slide, but very basic. Now, once this application gets injected by Lumigo, by the Lumigo operator, with our tracer, this is how the kubectl describe is going to look like. Now let's walk through the interesting components here. The first interesting component is we add an ephemeral volume, right? An MTDR volume. Now, just to remind everybody, an ephemeral volume is a volume where the lifespan is like the lifespan of the pod, right? Unlike a persistent volume, this volume dies with the pod. So we add this volume. Then we add an init container. And an init container is a container that starts and completes before the app containers even start. So it starts and completes before the app containers even start. And this init container has an image. That image contains our tracers, the Lumigo tracers. So the init container spins up with the tracers. It copies the tracers into the ephemeral volume that's mounted to it, the ephemeral volume we saw a second ago. And then it completes. Now, the same ephemeral volume is also mounted to the app containers. So the app containers start with the tracers in them. Now, there's an interesting question here, which is, how do we know which tracers to copy into the containers, or into the ephemeral volume? How do we know if it's Java, Node, Python, etc.? The answer is, we do not. So we copy all the tracers. Now, we'll get to a point where we actually do care what runtime is running in the container, but this is not it. Right? Here we don't care. It doesn't really matter. We just copy all the tracers into the ephemeral volume. No real downside here. And lastly, we add 3 environment variables. The first one is the LD preload envar, with the path to the Lumigo injector file, which we also copy into the ephemeral volume, and we'll get to that later in this talk. We have the Lumigo tracer token, which is just the means of authentication to the Lumigo backend, and we have the Lumigo endpoint, which is an endpoint to a service in the operator for an OTLP collector that receives, processes, and exports the trace data, right, to the Lumigo backend. So, how do we get the tracers into the containers? Covered. Now, we're getting gradually more interesting as we progress here. How do we activate the tracers? How do we load the tracers into the process? So, as we said before, we don't want our users or customers to touch their code as they do this. So luckily for us, there is a way in every runtime is different, but in every runtime there is a way to basically load packages through environment variables. So that's what we do. And as an example, let's look at a Node example. Node has the Node 8 and up has the Node options environment variable, and we can basically append to it -r Lumigo/OpenTelemetry. -r is short for the require statement. And so adding this statement to the Node options environment variable is effectively like writing the line beneath, right? So just like writing Lumigo equals require path to the package. So this is an example for Node. We do this for Python. We do this for Java as well. Now, how do we set the right envar on the right process? This time, it's not a trick question. We actually care this time, because unlike before, this is visible to the user. Right? We don't want our users to start debugging a container which was running a Python process, and for them to find on it a Node environment variable, the Node options envar, and start thinking to themselves, why is this here? What's wrong? Does this have Node? Does this have Python? This is confusing, right? So it sounds trivial, but we had to find a way to solve this. We can't add all the envars. We have to add the envar for the specific runtime that is running inside that pod, that container. So to understand how we do this, we have to dive in a little bit into how runtimes like the Java virtual machine, CPython, and Node actually work. A quick detour, but we'll come back very shortly, I promise. So there are two major ways to compile applications, right? There is statically compiled applications and dynamically compiled applications. Statically compiled applications result in an application, a binary mostly, that is self-contained. It includes all the packages, all the code, all the libraries that it needs in order to run. It does not rely on anything external. Dynamically compiled applications are different. These are how most applications are compiled, and they actually rely on external libraries, on DLLs. Now, why do we care? Why am I telling you all this? Because, and we're getting there, because there is a library that's called libc, the C standard library. This library was developed initially as a helper library for C applications, but very quickly it spread into virtually all operating systems, and virtually any runtime relies on it. Now, what does the libc do? Libc has basic operations, right? So mathematical operations, string operations, memory management, I/O, and it also has a very interesting function called getEnv. GetEnv is a function within libc that gets as a parameter, as a variable, the key for an environment variable and returns the value. So effectively, any application uses getEnv to request the value of an envar. Now, you can start to see where I'm going with this. So if we had a way to hook into libc and basically control the value that it gets and receives, we would be able to set the right envar for the right process. Now, the way we do this is, if you remember in that pod spec that I showed you, we had the LD preload environment variable directing to the Lumigo injector. That is basically telling that process to go and look for and replace basically libc with that Lumigo injector SO file. And so what happens here is the Node.js process spins up. It looks up the node options envar, in this case, assuming this is a container running a node application. It makes a call to the Lumigo injector, as opposed to libc, to request for a call to getEnv with the node options key. It looks up the actual value. It appends to it -r Lumigo/OpenTelemetry, and it returns that complete value, right? The node options, the original node options value appended with -r Lumigo/OpenTelemetry. And the end result is that it's effectively like the user had written require Lumigo/OpenTelemetry in their code. Now, keep in mind, Lumigo injector, if it gets a call to getEnv with any other envar that we don't care about, it just gets the actual value and passes it along, right? So it doesn't do anything to it. But if and when it gets node options, Python path, etc., something we care about and need to alter in order to load our tracers, then we append the value and return it to the process. OK, so this is how we activate the tracers. Now, how do new pods get automatically injected? How does that process look like? So we use something called an admission controller mutating webhook. And this is basically a construct in Kubernetes that lets you modify incoming requests to the Kubernetes API before they are acted upon. So what happens is this. Create new pod or deployment comes into the Kubernetes API server. They say, wait a second, I want to see if the admission controller mutating webhook wants to do something about it. They refer to us. We instrument the template to insert all the stuff we talked about, the init container, the ephemeral volume, all that stuff. Once we finish, we tell the Kubernetes API server we're done. And the Kubernetes API server proceeds with creating the new object. Now, keep in mind this is a blocking request. We want to make sure that we don't break anything in the cluster. So we do two things. First, we have a continue on fail setting. So if we aren't able to do our operation successfully, it doesn't really affect the creation of the object. And also, we have a timeout of 5 seconds to ensure the same thing. OK. So this is how we get new pods automatically injected. Now, how do we clean up after ourselves? We use a Kube API watch. Here we elected for a non-blocking operation. Our operator sets up a watch on the namespace where the Lumigo object is set up. And basically what we do here is once the object gets deleted, the Lumigo object gets deleted, then we get a notification. We watch for that. The operator goes and uninstruments all of the pods. So it goes and removes pod by pod all the Lumigo tracers. Eventually, it also removes the watch. So step by step, basically removing every trace of Lumigo in that namespace where we deleted the object from. OK, so we're done. Made better time than I expected. Quick summary. So getting the tracers into the container, a combination of init containers, ephemeral volume. How do we activate the tracers? We use a trick existing in every runtime where we alter the envar using the LD preload to basically inject the Lumigo injector to hijack the get-env operation. And how do we get new pods to get automatically injected? How do new pods get automatically injected? We use the admission controller mutating webhook to do that. And we use Kube API watch notifications, very simple, to clean up after ourselves. Now, I hope this kind of a little bit added something to each of you and kind of opened your eyes to how you can automate and make seamless operations, which otherwise would be relatively complex using a bunch of Kubernetes constructs. And we're out here on the floor. If you have any other questions, happy to field them. And enjoy the rest of the day. Thank you.